Hello everyone, today we would like to present our project entitled Design and Implementation of an IoT-based smoke detection system using ESP32 and MQ-135. This project focuses on developing a simple early warning system to detect smoke and send notification using an IoT platform. My name is Najwa Aulya Rahma, and together with my group members, Enka, Putri, Laili, Azzaria, Feivel, William, Audie, Stevianto, Adesya, Yafi, Aristawati, and Talitha, Iftinah, Budiona, we will present this project.
Early humans lived nomadically as hunter-gatherers, facing predators, cold nights, and raw food. To survive harsh conditions, they used animal furs for warmth. A major breakthrough came with the discovery of fire, first created accidentally through friction between stones or sticks. Fire changed human life by providing heat, protection, and a way to cook food. Over time, its use expanded. During the Middle Stone Age, fire helped produce stronger tools, such as heated silk blades. In the Greek Dark Ages, fire evolved into a weapon, including early forms of Greek fire. The Industrial Revolution marked another transformation. Fire-powered steam engines, from Newcomen to the improvements by Watt and Bolton, driving industrial growth. Today, fire supports modern industries, but also causes destructive wildfire worldwide. Because fire remains both useful and dangerous, early smoke detection is essential to warn users and prevent uncontrolled fires.
Methodology, the system overview. In general, this electronic system to detect smoke consists of ESP32T and a single MQ-135 smoke sensor, where the main purpose is to have the device to send signals through its wirings in the form of digital signals to the ESP32 microcontroller, where it transfers the signals to the cloud. In this case, we use Blynk IoT, which in turn would send a notification to electronic devices that we use every day, in example, a smartphone, laptop, etc., that contains warning of smoke being detected. Then hardware component. The hardware used in creation of the smoke detectors comprises of first MQ-135 smoke sensor. It used to detect smoke through resistance change on heated as an O2 surface and compares analog gas signal with threshold to give on-off output. And ESP32 used to read sensor signals, filters data, detects smoke spikes, sets alarm thresholds, and converts analog value to ppm and connects to Wi-Fi to send alerts. Then power supply. ESP32 powered by 5V from laptop USB and MQ-135 powered from ESP32's 3V 3-pin. Then couple male-female and female-female cables connect ESP32 pins to the sensor module. And last, breadboard for reusable platform with crosswise and lengthwise metal strips for easy wiring.
So, hello everyone, and okay, back again with me. This is the ESP32D, and this is the MQ-135. Why are we using it? Seriously, why? We use it because we are using it as a smoke detector. These two components are vital. And if we see this ESP32, it uses CPIO 32 ground pin, and also the 5-volt pin denoted by the blue one. So now let's think. Why? And how does it work? Yes, it's a good question. Why and how? Why do we use it? Because we know that smoke in buildings or in environment where it is prone to fire is dangerous, a hazard. And therefore we need a smoke detector that is cheap, yet at the same time it works. That it works, just works. And so, without further ado, let's get into this. So when smoke enters the chamber within the MQ-135, it produces a change in the gas variance, the gas properties, the gas. So when the gas is entered here, it will be turned into an analog output, denoted by the black one, the black cable here, towards CPIO32. And from the CPIO32, the ESP32D will process it into a digital output. And from the digital output, it will be sent to the server that is Blynk, thanks to the ESP32D's capability of being connected to the internet. That is why we have here Wi-Fi. See, Wi-Fi. Wi-Fi. 2.4 giga. Okay, continue on. And we also need to know that this MQ-135 is powered by 5 volts. That is why this cable here, although currently not connected to the laptop or something, the USB port of a laptop provides 5 volts. And from this 5 volts, they will be connected to this 5 volt cable here, 5 volt cable, the blue one, into the red positive charge strip of metal underneath the breadboard that will be shared with the red cable here, going to the VCC of the MQ-135 over here. Red cable, remember, red cable. However, all components must have a ground, because without ground, it will short circuit. So the ground from the SP32 is denoted by the white cable to the negative blue rank-wise strip of metal that serves as a ground, the 0 volt of everything, where the electrons will move to the blue ones. And from the blue, we can also see there is something that shares it. Yes, see, it's green. The green cable is located just one hole to the left from the MQ-135. And once more, I must reiterate, we do not use the digital output of the MQ-135, but only the analog output denoted by the black cable. And for the rest of the process, as I already mentioned earlier,
From the live testing results shown in Table 1, the MQ-135 sensor readings vary depending on the presence and intensity of smoke. When no smoke is present, the sensor value remains relatively stable around 1043, which represents the normal air condition. As smoke begins to appear, the sensor values gradually increase but still remain below the detection
threshold, as seen in the range between 1205 and 1847, where the system continues to classify the condition as normal. Once the smoke concentration becomes higher, the sensor readings exceed the threshold value of 2000, with recorded values such as 2162, 2192, and reaching a maximum of 2999. At this point, the system consistently changes its status to data detected and sends a notification to the user. When the smoke concentration decreases, the sensor values also drop, and once the reading falls below the threshold, such as the value 1999, the system returns the status to normal. This behavior indicates that the system responds dynamically to changes in smoke concentration and follows the predefined threshold logic correctly. From the table, it can be seen that there are occasional fluctuations in the sensor readings, especially in the range of 1347 to 1716, and also between 1847 to 2162. These fluctuations show that there is a slight decrease in the number of gas particles sensed by the sensor, even though smoke is still present. This condition is most likely caused by window or airflow blowing in the opposite direction of where the sensor is facing. Because of this, less smoke enters the sensing chamber, which explains why the sensor readings fluctuate. When the sensor value goes above 2000, the system immediately sends a notification indicating that smoke is detected. This notification is sent through the Blynk IoT application and also to the user's Gmail, so the warning can still be received even if the application is not open. On the other hand, when the sensor value drops below 2000, for example at 1999, the system sends another notification showing that the condition is normal and smoke is not detected.
The smoke detection system utilizing an MQ-135 sensor and ASP microcontroller successfully detects smoke and provides early warning to the user. The sensor reading increases as more smoke in the present, where the value above 2000 indicates smoke detection and the value below 2000 indicates no smoke. Through Blynk IoT, the system also supports more remote monitoring and the real-time notification during potential fire hazard. Although the prototype still requires proper sensor calibration is effective by environmental factor. It effectively demonstrates IoT-based early warning tool that can enhance safety and help reduce fire risks. This brings us to the end of our presentation. Thank you for listening and we appreciate your time and attention. Thank you very much.